Hello, this is Adam Pilchak. I am currently the Director of Aerospace Materials at Materials Resources, LLC. And today I have the distinct pleasure of interviewing Rod Boyer for AIME's Oral History Project. The date is March 31st, 2022, and this is a second interview following up from another one we did December 9th, 2021. Rod Boyer is a longtime member of AIME and TMS, had many contributions to the field of titanium metallurgy and the aerospace industry. He finished his distinguished career as a consultant under his business RB Ty Consulting. And today we're going to talk a little bit about his experiences throughout his career and during his time growing up. Can you tell me about where you grew up?
Yeah, I grew up in a city called Aberdeen in the state of Washington, 2-hour drive from Seattle. Well, I had one brother and a stepsister, and they were the youngest, and they're all gone. I worked at a pulp mill Monday through Friday, and then I got 3 days off. And then the next week I worked swing shift. And then the next week I moved to graveyard shift. And I didn't really appreciate that very well. So that's why I knew I was going to be an engineer. Worked for a year and a half after I got the degree at Grace Harbor Junior College. So that's when I decided I don't want a 9-to-5 job or 8 hours every day. And finally got a chance to get into University of Washington. Got my bachelor's in '63 in metallurgical engineering.
What made you choose the University of Washington?
They had a good engineering school, and it was relatively close and not as expensive as some of the others. So that's what took me there.
Were there any particular professors there that were very memorable to you? Anyone that influenced you in any particular way?
Probably my thesis advisor, Dr. Douglas Polonis. And I remember in a blackboard, he could draw almost a perfect circle.
That's quite a feat.
I had a professor and when I had a lab, I got put into trying to get single crystal zirconium. I went it through the cycle and it got contaminated, and I sarcastically said, geez, it looks like we rusted it. And I had a little thing about maybe 1/8 of an inch thick, a little cross section of the circular rod that we were using to change the temperature from one end to the other. And the professor, he saved a slice of that thing, and he had it on his desk for about 30 years. He came to an ASM meeting. I think I was talking. At the end of the thing, he gave me that little piece. He had it sitting on his desk for 30 years, and he remembered what it was from. I was kind of amazed with that.
You shared the same advisor as Jim Williams. Any other memorable classmates from that time?
The only ones I can remember is the guy who was in my high school class, but he's the one who told me take metallurgy. We have quite a few good students, but Jim was the best.
Out of grad school, did you go straight to Boeing, or did you have any other jobs first?
I got invitation to work from Mesa Rockets, solid rocket motors. I started there in '65, and apparently they pissed off the Navy. They started into layoffs. And my understanding is it went from 20,000 to about 2,000 people in a couple of years. So I got out of there. I got a job down in California, and then they had a layoff, and I'd only been there a couple months. And their policy was if you hadn't been there 3 months, you were automatically laid off. It just happened. I had an application in at Boeing. Just about the time that these guys laid me off, I got a telegram offer from Boeing. I had that offer, so I gave myself a week to look for a job, and I took the offer and drove up to Seattle and went to Boeing. Jim was really got me into becoming useful. I worked with him in research on titanium when I started the supersonic. And so I became an electron microscope guy. Jim and I did a lot of 2 or 3 years on that. And then I became a metallurgical engineer after that program faded, and worked in failure analysis and met lab and electron microscopy. the mid 70s when I started being the lead engineer. That opened up the door for me to do a lot of traveling, approve processes and approve new suppliers, approve castings, forgings, all that kind of stuff in every part of the world except South America. And I got trips to Australia and New Zealand, all over the US, all over Europe. I got to Moscow and St. Petersburg. And anyway, I've been all over the world, even in Africa.
What were some of the most memorable programs for you that you worked on?
Well, I worked on the SST with Jim.
That's the supersonic transport?
Yeah, I got a lot of articles, but this is probably my biggest effort. I think it took about 3 or 4 years to get there.
Every titanium metallurgist on the planet appreciates that book right there, Rod, no doubt.
I became the titanium lead engineer. This really set me off. I already pretty familiar with titanium and had a fair amount of information about it. But that was really the start of my career, because between Boeing and my consulting work, I was in titanium for probably about 50 years.
Titanium, what's unique about it and some of its interesting characteristics and applications?
Titanium is a unique material, but it's very expensive. And so we're constantly doing work there so we can reduce the expense, because it's an excellent weight saving component. In addition to a low modulus has advantages for springs. It's an excellent material for aerospace, chemical, petrochemical, biomedical, architecture, and special niche stuff. In aerospace, the primary thing they're competing against is aluminum and steel. You have to have a really good process to replace aluminum, because aluminum's got a weight advantage. Against steel, titanium has an advantage of about 40% in density, but it again is expensive to work with. So that's where most of the work is done, is developing alloys, processing, which enables us to get there.
So given that titanium is so expensive, you must need good rationale for its use. You mentioned certainly weight savings over steels and the low modulus to help with springs. Are there any other reasons one might consider using titanium in aerospace applications?
Temperature, you can go a lot higher in temperature with titanium than you can aluminum. Steel, you fighting the fact that the steel is lower than the titanium. And that's why we have to develop better alloys or processing means to get the higher strength so that you can make the gain and improve the life of the alloy. Steel and aluminum have pretty good corrosion problems, and titanium is excellent, but we got to develop ways to now tie them together so we can take care of that weight advantage. Composites compatibility is another big factor. More composites going in to aircraft, and titanium is compatible with the composites much more so than the aluminum. Sometimes you just use it in a joint, or joining it against aluminum or steel against composites. If they can do it with titanium or aluminum, that's probably the cheapest way to go. Got the lower modulus, so that means you can go longer time in service and you reduce weight. And we use a lot of titanium in springs. Stainless steel, you can bury that in the ocean and it will eventually, after a number of years, even the stainless steel pits, whereas the titanium does not. You just have to be careful about making sure that you haven't got abrasion going on or something someplace, which will reduce or eliminate the oxide and corrosion proceeds. Operating temperature, titanium obviously better than aluminum. It's not as good as in aerospace applications. A standard alloy, you can't use it for a very high strength because the strength will just be reduced by the heat. But we've developed higher temperature alloys with addition modifications so that the oxide there, they can compete with the steels up to about generally 1100, but there are alloys which go to 1200. Some we use for short times at high temperatures titanium, 15 vanadium, 3 aluminum, 3 chrome. I didn't mention the space limitations. We had a part on a 757 where the wing design is set, and then they come to build a part of the wing, and they find that the aluminum that they're trying to use isn't strong enough, and this higher strength, low modulus allows the titanium to be used in those kinds of conditions, and it survives quite well.
It's been said that you're responsible for putting more titanium into the air than anyone else. One of the largest structures, one of the most important ones that you've done is introduce titanium landing gear. Gigantic structures, they're very difficult to produce and process. What kind of challenges did you encounter when trying to field titanium landing gear?
One of my prime development of the titanium 10 vanadium 2 iron 3 aluminum alloy, which can be heat treated to 180 degrees. It's melting difficulties, etc. With that strength level, you can't tolerate very much anything or it'll generate a crack. But we had a few years of experience with the 57 and its smaller parts, and the landing gear guy for the 777 actually selected it. He saw the properties, and people were really anxious about it at first because of melting problems, defects, this kind of thing. Because at that high strength, they're going to be big factors. We really jumped in, and you can see that all those named things are titanium parts, titanium 1023 parts, and they show how we get that weight saving.
And which alloy was that, Rod, that you said that you developed that reduced that weight?
1023.
Did you work on the SR-71 program?
No, data that I've gotten from Lockheed. We needed an alloy which could fly at high altitude for a spy mission. SR-71 was a first supersonic titanium of note, and it's also resulted in the fastest and highest flying attributes. This is because they developed a beta alloy, what we call a beta alloy, which has got a higher beta content so that you can strengthen it. So titanium was used on airframe and all the wing and skin structure. And that airplane flies at 3.5 Mach at about 85,000 feet. And it's painted with radar absorbing black paint. I've talked to SR-71 pilots, and they say when they go over Russia, they fire a rocket and they just turn on the fuel and outrun the thing. So they work very well.
There's probably a small number of people on the planet that have taken an alloy from the development phase to putting it on an airplane. You did that multiple times?
Yes.
That's incredible.
And I'm not the smartest guy in the world, but I seem to have a knack for picking things that work. That was my bubble, to be able to develop new materials. 70s, 80s, and probably at least the early 90s. I think I did more for the titanium industry and the aerospace industry than anybody. I developed several new alloys for strength, for superplastic forming, for formability, castings. I developed more products for than anybody I've seen yet.
Is there one accomplishment, one thing that you have flying that you're like, that's the one, that's the most important one I did?
And I took beta 3 and made springs out of it. And that's with the fact that you got half the modulus, and that means you need half the coils. So now you can actually make them cheaper than steel. Ever since I developed that, we've used titanium springs and landing gears.
So Rod, were you a member of any technical societies?
Oh God, yes. I was always in ASM and TMS and AIME. I was definitely involved, and I was probably most heavily involved with the ASM.
On some of the, maybe on the committee?
I was always also on the board for ASM.
And I think you were a member of the TMS Titanium Committee for a long time, if I'm not mistaken.
Yeah, that's true. Probably 30 years.
When you stopped being the liaison to the International Titanium Association, so you were a really long-standing liaison between those two organizations. And now since then, we've struggled to keep somebody in that for more than a year. That was a great service you did back then.
Well, I appreciate it.
One award on the list here seems like a little bit of an oddball, so I'm going to ask about that one first. You've had this wonderful career putting titanium all over aircraft, but in 1994, you received the ASTM Russ Ogden Award for contributions to reactive and refractory metals. So I'm curious about your work with the reactive and refractory metals.
I don't even remember much about that.
All right.
I mean, there's only one system that is really good, and that's titanium.
Yes, sir.